So this talk is joint work with Davide, Luke, and Tinne at KU Leuven. Not surprisingly, the kind of problem setting we're interested in is stochastic planning, right? So actions can be stochastic. The states can be mixed, discrete, or continuous. But perhaps one of the twists that we want to look at, and I'll substantiate this by examples, we want to conduct search over growing and shrinking spaces, and that's motivated by some applications we were looking at. Mathematically, of course, we are thinking of a Markov decision process, right? We're trying to compute a policy which maps states to actions. And typically what you are is you might be in a state S at a time point t, and you're doing an action, and you have a distribution of potential states you could jump in. And depending on the action you take, you get a reward back. Right, so that's the idea, and your objective might be to maximize the expected reward over some horizon. We're always thinking of finite horizons in this work. You might have seen expressions of this form. Essentially what this says is that the value that you have for a particular state given a policy is basically the expectation over the sequences of the remaining time steps left. And what you're trying to do is compute, the action at a given state that provides the maximum, that maximizes this, this expectation over your time steps. So far it's fairly standard. The point we sort of wanted to make here is that, it's a really elegant mathematical framework that applies to a bunch of settings, but solving the general case, by general case I mean that when you have states and actions that are both discrete, continuous, and mixed, it's notoriously hard, right? And sort of the other observation we made was, even though they've been well studied, actually writing down these MDPs or very complex applications turns out to be very challenging. So what got us thinking is that, we might want to have a rich modeling language, that allows a transparent domain axiomatization in the presence of unknowns and stochasticity. And we wanted to come up with a solution scheme that leverages the structure, right? There's no point providing a really rich language, and when it comes to computation, we just throw our hands up in the air and say nothing's possible. So we wanted to come up with a, kind of a solution architecture that really leverages the structure. And when we looked at what we know in terms of very general planners, right? One of them is sparse sampling from, going back all the way to 2002. So it's a very general scheme of how you could, construct a sampling-based planner for MDPs, but there's no consideration of structure. So it's fairly abstract, and perhaps that's one of the reasons it's fairly slow. Another sort of more, recent planner is PROS, which is based on UCT. Now this is a discrete planner, so there is a way you could take a continuous domain, possibly make it discrete, and use PROST. But what they do note in the PROST work is that, it's not perfectly suited for circumstances we're facing probabilistic planning, because it just takes a model space abstractly and doesn't really exploit the probabilities. So where this turns out to be really crucial is when you have continuous distributions, right? Often if you look at a Gaussian, all your samples should be centered around the mean, and taking samples from, the entire space is completely impossible. If you just throw away the probabilities and just look at the space of values, you have an infinite space or uncountable space. So not exploiting the probability seems like a mistake, and that's what really motivated our work. So the work is really contextualized in these kinds of programming languages called as probabilistic programming. These are languages basically to model structured probability distributions. One of the reasons that these languages are now becoming popular is that machine learning is made up of multiple components, and you might want to modularize and compositionalize all of the different components. So you think of them as programs. You think of each machine learning entity as a program, and probabilistic programs can put these together. If from a mathematician's point of view, you think of these as programming languages of the stochastic primitive. So, in Python, for instance, you might say some variable gets a certain value. In a probabilistic programming language, you're going to say this variable is drawn from a distribution. So that's the change. There are many languages to date. The language that we based our work on is an extension of Problog, if you've heard of it. But if you're not, I'll try and give you an example of what you can do with the syntax. Okay. So imagine now the situation where I'm facing this room with a whole bunch of blocks. Okay. They're all wooden blocks, but they are of different colors. And I want to say that when I go into the room and pick up a block, it could either be black or brown. Okay. So the way you would say this is if X is wood, then the color of it is drawn from a uniform distribution in black and brown. So far, so good. Now imagine a slightly more complicated situation where the same room is filled with both metallic and wooden blocks, okay? I'm picking a block at random, and by looking at the space of all wooden blocks, basically what it follows is what is called as a beta distribution, so the one on the bottom graph. So what you're saying is that if X is wood, right, its size is drawn from a particular beta distribution. On the other hand, if X is metal, right, it's drawn from another distribution. Okay, so you have these two clauses, and then you have some number, right? So let's say I draw 6 or 7 blocks. So let this number be n, and then I'm going to say that if I take out 6 blocks, the distribution on the kinds of the blocks in this set follows some distribution. So 70% of them are going to be metal and 30% wood, right? So these are basic. This is basically to provide a very complex probability distribution, which if you had to write down the joint, this would be really taxing. But with a language like this, it becomes fairly simple. I could take this one step further, and I might be unsure about the number of blocks I take. So imagine, for instance, you're trying to tell a robot to navigate itself in a room full of people, but you cannot tell the robot exactly how many people there are. So what you might want to do in this case is you might want to say the number itself is drawn from another distribution. Okay, so you can deal with states where a lot of unknowns are present, and you can provide stochastic primitives to essentially capture the situation. So the language can be used to talk about Gaussian models, Gaussian noise models for acting and sensing. It's not very difficult to do, but one of the things that we were able to do with a language like this is basically talk about object tracking. So, in computer vision, object tracking is a big, domain where you're basically thinking about, finding out the objects in a scene. But what we're able to also do here is talk about the causal relationship and the commonsensical relationships between these objects. For instance, in this case, what's happening is that he's dropping one of the boxes into a bigger box, and of course it falls in. And what this means is that at this situation, at the second scene, although the vision system can only spot one block, it implicitly knows that there are actually 2 blocks, and the second one is inside the first one. Right? So you can really do very interesting things with these kinds of languages. In the context of planning, what really motivated us is that we wanted to talk about providing goals when you don't actually see some aspects of the goal. Okay, so in this case, I'm telling the robot to find the red can, but of course there is no red can in the beginning. So what you can do is you can provide a stochastic model of this sort, which says that if I remove an object, right, and it happens to be a box, the number of objects behind it is drawn from some Poisson. In this case, it's a Poisson centered around 1, which means that there could be no objects behind the block, but there could also be one or more objects behind it. So from this point of view of search, what is really happening is that if you look at the left branch, the robot picks up the blue box, right? And now what's going to happen is that either there is no red can still, so it's the leftmost branch, or there's a red can next to the green can. Right? So it's essentially search, but you're searching without knowing what to expect, right? And similarly, if you look at the right branch, what's happening is that I remove the yellow can, and maybe there's nothing behind the yellow can, or there's a red can, right? So you can define goals of this form, and that's one of the experiments we did do. For those of you who are interested in how this really works, essentially it's a combination of importance sampling and SLD resolution. Now the question is, inference is well studied for these languages, but planning is hard. So it's not the specification of the planning problem that's hard, because you can always specify these time index conditions to basically say what are the conditions for making an action true, what are the reward functions, and so on. The question is, how do you actually plan with it? So the way we approach it is that we do importance sampling, basically because it's such a large space. If you think back about the value function, which tells you the value for a given state, right? There's also what is called as a state action function. So essentially, you tease apart the possible actions you can take, what the algorithm does is basically it samples episodes, okay? It samples the trajectories of these MDPs, and essentially it constructs a greedy policy to figure out what is the most optimal action to do given the samples you have taken. Again, realize that these samples are weighted, right? They use the distribution, which means most likely you will pick the samples that matter the most, okay? This is I mean, again, too many details in the algorithm. I'm going to skip over the small parts, but essentially the main idea is that you do important sampling, pick the optimal policy, and constantly iterate, refine this as you sample more episodes. So it is substantiated by some analytical work. All of the details are in the paper. From a high-level point of view, one of the key differences between the planner we propose, which is called as HYPE, from normal sample-based planners is that, as I mentioned, usual sample-based planners only use a model to generate samples without actually exploiting the probabilities. They store the Q function, which is fine, and they do function approximation because the space is so dense. We don't do any function approximation. I mean, you could think of importance sampling as a kind of approximation, right? Because there is a proposal distribution guiding your samples, but there is no real function approximation. I'm still okay on time, I think. And what we also do is we store the V function and evaluate the Q function based on the probabilistic model. To test this work, so as I mentioned, we've been testing this language on a number of different domains, including particle filtering, affordances, and so on. But in the planning context, and especially the MDP context, we wanted to look at a bunch of domains. So we picked two discrete domains from IPPC, one continuous one, some hybrid, and also one experimental setup with an unknown number of objects. And we, of course, varied the dimensions to see how scalable it is. What we basically observe is that in almost all the cases, right, so just to pick the very first domain, for instance, what you see is that we are, if you compare it to SST, we are getting substantially a higher reward, and almost always at 1/3 or 1/4 the time that SST takes. There are a couple of reasons why this is happening. This is some more comparisons between HYPE and SST. A couple of reasons why this is happening. One of the key things we think is that perhaps the structure is really helping constraining the search space, right? Because if you expand out the entire search space, it is massive. And of course, SST, as I mentioned, is dealing in the abstract setting, so it expects this blown up search space. So in a way, we are saving a lot by not really expanding this entire search space. And of course, using these samples and doing this kind of weighted importance sampling is really helping us converge to a very good policies fairly quickly. And of course, if you go to the setting where you have these unknown number of objects, the one I mentioned where you're trying to find the red can, the situation becomes more extreme. Because essentially, in this case, you're dealing with a Poisson, so the state space is enormously large, and we often see that the planner is able to do very well with a very short period of time. Now, the fact the fact is also that the language has relational features, right? Because you're describing everything in using first-order variables. So one of our interests was, could you push this even further? Could you use the fact that you have this, this relational language to essentially constrain the search space further? And indeed, we can use regression. So regression is a symbolic regression is a well-known technique where basically you can do backward reasoning on on plan paths. And we were also able to see that you can scale up the number of objects in your domain arbitrarily, right? But the key benefit of using a first-order representation is that you don't really have to instantiate the variables for all the domain elements. So what we often see is that as you increase the domain size, by regression, we're able to somehow constrain the amount of time it takes while still getting substantially good rewards as opposed to the ground planner. So to conclude, we have this, we worked on this fairly general planner called HYPE, which works in a variety of settings, including discrete, continuous, and hybrid. It exploits the probabilistic model, essentially, to do weighted importance sampling and the relational language. So there is this whole body of literature in probabilistic reasoning called lifted reasoning. We haven't really exploited the full power of that, of that literature, but I think this is the first step to essentially see how this relational language can be useful in different probabilistic settings. And as I mentioned, the performance is almost always better than SST, while still supporting a very powerful language. Perhaps the key thing is that it's not just for planning, right? The same language has been used for object tracking and rule learning. So you can think of planning as part of a larger pipeline where a bunch of these other applications are going on, and planning would incorporate this as a part of its a general framework. Thank you very much. Yeah.
There's time for some questions. Christian's ready. He's eager to throw, so. Sheila.
Perfect.
Hi, nice talk. This is a fairly specific question, and I'm just curious. So of course, as you know, when you have a mixture of Gaussians, for example, you can use closed form solutions. You can use and people use Kalman filters, and when you don't, you often use some sort of sampling. But there's a beautiful middle ground, which is manifest in things like Blackwellizing filters, where you combine a closed form solution with sampling where the model's not exact. Have you thought about that in the context of this work, and is that something that you can leverage?
Yeah, so that's something we have thought about. So we did think about it a lot, and I think there is a way to do it, but it's just not entirely obvious what's the most effective way of realizing it. So there's some work in the probabilistic logical literature on how you could do Rao Blackwellization. And I think we could potentially lift some of those ideas, but we don't have a solution yet on how that could be done. But yeah, that's a great point. That's in fact a great middle ground for doing this. Yeah.
Great. I have a different. If nobody else has a question, or I can. Okay. Is it you? Who, can you raise your hand if you want the mic? I'm not sure who wanted it.
Ask another one.
I can ask.
Sure.
Okay. So I was just curious about the different types of distributions that you thought you needed to model typical planning languages. So I noticed you had Poisson distributions and beta distributions. Can you comment a little bit on that?
Yeah.
And I'm also curious about how it relates to these. I remember when I was an undergrad, I had to build simulation systems. And those used Poisson distributions and other systems, and I was wondering about whether there's any relationship to that very old work that's done, for example, in simulation and queuing theory for networks and various other things.
Yeah, so I guess that's a great question, and this is, I guess, a question for anybody thinking of using these kinds of more complex distributions. What's the space of family of things we need to consider? Again, the observation we made is that often Gaussians, beta, and Poisson are kind of the largest, or you could have something like a logistic function. So I think these four things are really useful for a bunch of domains. Now the thing about using, say, for instance, you can always fit some kind of arbitrary distribution as a Gaussian. The question is, what do you lose out on? So there is some work right now on trying to understand the loss that you get by force fitting, more complex data points to some given family. So we started doing some work on what are called as piecewise polynomial representations, which do offer some robustness guarantees on how close you are to the full distribution. So I think there is a loss when you do everything as a Gaussian. And sometimes maybe this loss is not substantial, like it doesn't matter, you can get away with it. And in some other cases, it could be that you're missing this corner case that essentially puts your application at risk, like self-driving cars, and then, something happens, and that's just one event you think that's never going to happen. If you put it in a Gaussian, maybe it's at the far end, and suddenly that's what exactly happens, right? So there is potential for understanding really the loss in
force-fitting
distributions. So the piecewise polynomial in that sense can be arbitrarily granular. So you have that flexibility, of course, but it's representationally more complex. So that's a trade-off. Yeah.
Thank you.
Okay, let's thank Vaishak again.